In this video, we're going to discuss how to find the value of a log expression without using a calculator. And we're going to rely heavily on the fact that the log function is the inverse of an exponential function. So let's start with a pair of inverse functions that we're more familiar with probably. So the functions y equals x cubed and y equals cube root of x. Those are inverses. And we know that when we compose inverse functions, so when we put one of the functions into the other, replacing the variable, they essentially undo each other is what I like to say. So if you have x cubed and then you take the cube root, those undo each other and you're just left with x. And we can compose them in the other direction as well. So we can start with cube root of x and then cube that, and still they will undo each other and we're just left with x. It's like if you start with 2 and you cube it, you get 8, and then you take the cube root, you get 2 back again, and vice versa over here. So this is going to be the case with the functions b to the x and log base b. If we put one of them inside the other, they're inverse functions, so they undo each other and we're just left with x. So here it's like we've taken the function b to the x and we've replaced the x in the exponent with the other function, the log base b of x. And so since we've put the log function inside the exponential and they have matching bases, that's important. Those values are both noted b for a reason. They have to be the same base to be inverse functions, but then that's just equal to x. And then composing them in the other direction would look like this. So we've taken the function log base b of x and we've replaced the x with the other function, and so composing them in that order as well gives us x. So this is going to be super helpful for us when we're evaluating a log expression without a calculator, because we're going to have log base something of a number, and if we can write that number as an exponential expression using the same base as the log, then that's going to help us see what this value is, because it's just equal to the exponent then once we have those matching bases. Now, since I'm trying to see if you can do this without a calculator, I want us to be able to see if you understand like what a log is and how it works. I don't want you to be hindered by the fact that maybe you forgot what 7 cubed is. I don't know what 7 cubed is off the top of my head either. So I've typed up this exponent table that I will give you on your formula sheet with a quiz or exam, so that if you understand how to evaluate a log, you're not stuck because you just are blanking on what 5 cubed is or something. So the base is over here and the exponent's here. So if you were evaluating 5 cubed, for example, the base is 5, the exponent's 3, and so 5 cubed is 125. All right, so let's practice evaluating these log expressions. So we want to find the value of log base 4 of 16. And since the base is 4, we want to rewrite 16 using a base of 4. The goal is to get it to look like this. So we have a base 4. 4 is our value of b, and so that input needs to be written as 4 to an exponent, because then whatever that exponent is, that's the value of the expression. All right, so we're going to rewrite 16 as 4 to an exponent, and you can use the table if you need to, but 4 squared is 16. We haven't changed the value of this expression at all. That's really important when you're working with any expression. You don't want to change the value along the way, because then you won't get the value you were trying to find. So 16 is 4 squared, so these are equivalent. We haven't changed anything, but we just wrote it in a different way, and now we can see that we have 4 to the x inside of log base 4 of x, and those are inverse functions. So they undo each other, and we're just left with the input, which was 2. So log base 4 of 16 is equal to 2. Look at the next one here. We have log base 5 of 125. And so since the base of the log is 5, that's the base we want to use to rewrite the input. So we're going to rewrite 125 as 5 cubed. Since 5 cubed is equal to 125, we haven't changed the value. And then we have inverse functions because we have matching bases. So this is just equal to 3. We have another example here, log base 3 of 81. Since our log has base 3, we're going to rewrite the 81 as 3 to an exponent. 81 is 3 to the 4th. And so then we can see that this is just equal to 4. All right, on to the next one. We have log base 4 here. So we want to rewrite 1 over 64 with a base of 4. Now this looks a little bit different than the ones we just did because the input is less than 1. If the input is less than 1, we've probably taken a reciprocal of the base. If the base is greater than 1 and the input is less than 1, then a reciprocal is involved. And we know a reciprocal comes from a negative exponent, right? Because 4 to the negative 1, for example, is 1/4. So then the question is, what do we raise 1/4 to get 1 over 64? Well, 4 cubed is 64, right? So if we cube both sides of this, 1 cubed is 1, 4 cubed is 64. And we have 4 to an exponent and then to another exponent, so we multiply those exponents, right? 4 to the negative 1 times 3 is negative 3. So 4 to the negative 3 is equal to 1 over 64 because the negative 1 first means we're going to take the reciprocal of 4 and get 1/4, and then the fact that it's a 3 means we're going to cube it and we get 1 over 64. So we haven't changed the value of our expression, we just replaced 1 over 64 with 4 to the negative 3, which we can do because those are equal. And now we can see, since we have matching bases, that this is just equal to negative 3. All right, here we have another example where the base is greater than 1 and our input is less than 1. So we can tell from our table or just from prior knowledge that 2 to the 5th is 32. But since it's 1 over 32, we've taken a reciprocal, right? So 2 to the negative 5 then would be 1 over 32. That's probably a little less convoluted than the way we did the first one. And so this is equal to negative 5. Okay, now the next one, the base and the input are both greater than 1. So we don't have a reciprocal this time, but the base is greater than the input, which was not the case on the first page. Right? 4 was less than 16, 5 was less than 125, 3 was less than 81. Now, the base is greater than the input, but they're both greater than 1, so no reciprocals involved here. But since the base of the log is 9, we need to write 3 as 9 to an exponent. And so you might be thinking, well, what exponent can I raise 9 to that would make it smaller, right? If it's not a negative exponent, right? We don't want to do a negative exponent because then we'll get something that's less than 1. So this is going to be a radical of some kind. If both numbers are greater than 1, but we need the exponent to make it smaller, that's going to be a radical. So we know that 3 is the square root of 9, right? 3 is the square root of 9. And so square root of 9 is 9 to the 1/2. Square root of 9 is just 9 to the 1/2. So 3 is equal to 9 to the 1/2. So we'll replace 3 with 9 to the 1/2, since 3 is the square root of 9. And now we have matching bases, and this is equal to 1/2. Okay, here again we have the base and the input are both greater than 1, so no reciprocals involved. But we need to write 2 as 8 to a power. And so since they're both greater than 1, we don't want to use a negative exponent. It's going to be a radical. So if you think about how these are related in terms of a radical of some sort, the cube root of 8 is 2. And cube root of 8 is 8 to the 1/3. So 2 is equal to 8 to the 1/3. And so this expression is just equal to 1/3. All right, we have 3 more examples here. We haven't done any natural logs yet in this video, but keep in mind that natural log, abbreviated ln, is just log base e. We discussed that in another video. Natural log is log base e. So this is what we have. And so we don't really even need to do any further rewriting because we can see those matching bases, and this is equal to 3. Okay, now for this one, we have log base 7, and so we want to rewrite the input with a base of 7. And so we're thinking 7 to what exponent gives us 1? And that's going to be 0. We've discussed previously any non-zero number raised to the 0 is going to be 1. So 1 is the same as 7 to the 0, and therefore this log expression is equal to 0. That's going to be something common that you see regardless of what the base is, right? Because any non-zero number raised to the 0 is 1. So if you have log base 5 of 1, for example, well, 1 could also be written as 5 to the 0, and so you're left with 0. So anytime the input of your log is 1, you're going to get 0, including natural log. Natural log of 1 will also be 0 because that's log base e of e to the 0. And so anytime you have an input of 1, regardless of what the base is, the value is 0. Because we saw on our graphs of our log functions that point 1, 0. That point always shows up on the graph of just a basic log function, regardless of what the base is. Okay, one last example here. Log base 9 of 9. Well, we have matching bases, but the question is what's the exponent, right? 9 is the same as 9 to the first, and so this is equal to 1. So that's a common pattern you'll see too. If the input is equal to the base, it's going to come out to be 1. So for example, log base 3 of 3 is log base 3 of 3 to the first, so that's equal to 1 as well. Same with natural log of e. Natural log is log base e, and we can think of e as e to the first, and so that's just equal to 1 as well.